Sometimes when we work with our on-premises networks and we try to connect them into the cloud, we're dealing with infrastructure and designs that have built up over 20, 30, maybe even more years in terms of their IP addresses and how they've been laid out. And times have changed. So once upon a time, the idea of using public IPs that you don't own according to the regional registrars within your on-premises green network here wasn't particularly rare. Whereas now we would try and definitely stick to the private RFC 1918 ranges, which obviously overlap with many other organizations. So sometimes we have to connect the green box into the blue box, and this legacy and inertia can sometimes get in the way. So let's talk about a customer scenario and how it was being solved in the interim, and how we maybe can optimize that with a design which perhaps you wouldn't think of when you first looked at this. So in this design here, we've got an on-premises green network, and they've got a WAN with thousands of branches connected, data centers, etc. And there's a sprinkling there of public IPs intertwined with private IP addresses. And there's thousands of prefixes here. Some of these spokes here need access to the green, some of them don't. It's not the entire range that needs advertising, etc. And the way in which the on-premises network team were dealing with this, let's say, uncertainty today, was to just advertise in a default route to Azure. So basically that was saying, send me whatever you like, and when it comes into our routers, we'll deal with it. We'll make sure that we route it to the right branch with the right public IP, and that way the people that run the green infrastructure, they don't have to worry about leaking through their public IPs internally through to the cloud provider. They kind of just say, send me whatever you want, and we'll deal with it. Of course, in the opposite direction, Azure will be sending all of the address spaces that it is using. And thankfully, the blue box here is just using RFC 1918, which has been confirmed unique across the organization. So it's sort of fair to say the use of public IPs is much more prevalent here because of the history. And generally speaking, it's very, very rare to find customers using public IPs here. But there are some niche scenarios where you may want to do that, especially if you own the address space and you bring it to Azure, etc. Anyway, so we're advertising in a 000 route for reasons of reachability on premises. We're not doing this particularly for reasons of filtering on premises. So this design here is sometimes referred to as forced tunneling. So you're forced tunneling all traffic back to on-prem. And that's often done to break out to the internet from on-premises through a centralized DMZ. So maybe you've got back on premises, maybe your center of gravity is still there, you're still moving to cloud, and the crown jewels of all of the filtering physical appliances of egress, IPS, IDS, etc. still resides on-prem. You may be doing this for those reasons. I'm talking more about the scenario where you're using public IPs on-prem for your local area networks. Okay, so now we move over to looking at the blue box here, and we've got a problem to manage, haven't we? Because typical design, the spokes are connected to the hub. They have gateway route propagation turned off, which means they won't learn the default route, but they will be sending all of their traffic at a centralized NVA or an Azure Firewall. And the Azure Firewall or the NVA subnet will have gateway route propagation turned on, so it will learn a default route. The default route comes into our edge, comes into the express route gateway, and then the Azure Firewall subnet in this example learns that it must send traffic destined for the internet to the express route gateway or the express route logical block as a service, and then back to on-prem. And that's a supported design. I mean, Azure Firewall has what's called forced tunneling mode, and what we do there is behind the scenes we sort of have multiple NICs on the firewall, one for management, one for data, and the management one sort of doesn't get subjected to that forced tunneling, and that lets the Azure Firewall control plane talk to the the service management elements, etc., without breaking your data plane. Anyway, the problem we have here is, well, we're just going to on-premises to get to these networks here. And of course, within the public address space, there's many, many other networks which exist. And some of them are Microsoft networks, Azure PaaS services, for example, Office 365, etc. And you probably don't want to go back to on-prem and go back to Azure, because that will break a lot of flows and kill your performance for a lot of services. So you have this challenge to manage of force tunneling this way, but wanting to send some traffic this way out of the firewall, effectively with next hop internet on the firewall subnet. So there's a certain degree of efficiency you can get by playing with the UDRs on the Azure Firewall subnet. And that's what I've seen a few customers do. They come into the Azure Firewall subnet. Again, remember, this is in force tunneling mode. And they say, I'm going to use the Azure Service Tags and UDR feature to say that anything in Azure Cloud next hop equals internet. And what does that do? Well, for example, if traffic comes from a spoke VM destined to the internet, goes to Azure Firewall allows or rejects that traffic, drops it on the wire, and the wire then has to send traffic to that public IP, and normally it would get sucked back to on-prem. But if it matches this service tag of Azure Cloud, which is basically every IP address used by Azure, it's going to do next hop internet. So that's going to get traffic destined to any Azure IP onto the Microsoft backbone as efficiently as possible. And there's a fair degree of nuance here, right? Because that Azure Cloud not only includes all Microsoft PaaS services, it also includes every PIP or public IP used by every other customer on Azure. So there's a decision to be made there through the lens of security and what you expect of your filtering firewall, etc. Maybe you're turning on IPS, IDS here in Azure for that. But that's going to get you part of the way here. It's going to basically be able to get traffic to Azure out locally without going back to on-prem. And there's another element to think about here, which is, well, if you're using public IPs on premises, there are certain services in Azure today which do certain things for RFC 1918, and if it's non-RFC 1918, it'll do other things. And the example I want to call out here is SNAT on the Azure Firewall. So if traffic comes into the Azure Firewall and it sends it outbound to a public IP, Azure Firewall is going to snap that traffic. And that's going to apply in this diagram whether it's going to Azure or back to on-prem. So typically in these designs, you get into the nuance of, well, I need to start editing the SNAT range on Azure Firewall. And the SNAT range doesn't support these service tags. So you end up having to capture all of the IP addresses that you're using on-prem that you don't want to snap for. And if that's a big long list, it becomes impractical to manage. So there's a few reasons why this design is tricky to manage. I mean, it all stems, of course, from this sort of intractable problem of these IPs, and ideally you want to get away from that. But if you know you can't get out of that hole, you want the let's say the least bad solution here. So this design I'm talking about, that's in play on the screen at the moment. It's got this snap problem to manage. It's got the same behavior applies to every spoke. So regardless of spoke type, it's going to be subject to the same routing behavior. Some traffic breaks out locally based on service tags. If it's not captured by a service tag, then you start having to manage lists of UDRs. You might run into UDR limits of 400, etc. So let's just step back and think, well, is there another way of doing this where the on-prem team can still advertise in a default 0.0, but we place some of the emphasis of control more in the cloud team in terms of what they route to on-prem and what they don't. Okay, I've changed my diagram slightly here. And what I've done is I've left the existing hub down the bottom here with the express route connected, with the firewall in place, with the peerings in place to the existing spoke VNets, with the user remote gateway turned on. That's important, of course, because they need that so that the spoke address space is still advertised to on-prem. So the default route leaks in here. And that's effectively as far as it gets, because we still have gateway propagation turned off in the spokes. So the Azure Firewall learns that 00 is via the gateway. We don't have any sort of UDR on the Azure Firewall subnet. We just leave it in forced tunnel mode. We change the NAT config on the Azure Firewall to something that's much easier to manage, which effectively is never SNAT. So we turn off SNAT effectively, because this is never processing traffic to the internet. It's only ever sending traffic to on-prem. What we've effectively done here is we've given control of how we route to on-prem to the spoke owners. So this won't meet every customer's use case, but for some customers where they have a discrepancy in how the owners of those subscriptions and spokes want to control behavior, this is an option. So in this model, let's say we've got a spoke here which needs hybrid access. And I mean, you could automate this if you wanted to, or you could give full UDR control to the spoke owners. All spokes have a 00 UDR go into the top Azure Firewall. So that's the centralized internet egress with the standard NAT config on it. All traffic goes there, all traffic goes out to the internet. Anything that goes through that firewall gets dropped onto the Microsoft backbone, and the policy here, which you configure, dictates what's allowed. This is the firewall that's which is used for east-west traffic as well between spokes. But if you want to get back on-prem, you have to effectively break the norm. So in this model, the norm would be you don't have access to anything on-prem. The only way you got access to on-prem is if you set a UDR going to the blue firewall. Because you send traffic to the blue firewall has a 00 forced tunnel back to on-prem, and that gets you into the world of whatever public IP you routed towards. If you don't set a UDR, which is more specific than your default, you go to the top box, which doesn't have access to on-prem. So some scenarios like this you might envisage, such as, well, you know, most of my spokes that I deploy are new applications, they live in the cloud, they don't need access to the green box, and we'll keep things nice and simple. We'll just force traffic out here. We got an internet egress DMZ in the cloud, and they've still got access to the other spokes if they need it. But this is kind of a hybrid disconnected spoke. Whereas if you have something else, maybe you have a VDI deployment or a more traditional Corp connected app, well, that goes in, let's say, a different category of spoke, which maybe you automate some UDRs that go back to on-prem, or you tell the spoke owners, well, depending on who you are, you talk to your counterparts on-prem and you route traffic to the firewall. And then maybe you would decide is this firewall just a IP forwarding device, or are you actually enforcing policy there? More common that this firewall would be in perhaps layer 3, layer 4, not IPS, IDS, such as this one, because it's controlling traffic to the internet. Anyway, the point of this video was to just show you an idea for, if you are managing IP addresses on-prem, and depending on where the sort of boundaries of control in terms of route manipulation sit, there are other options to simplify things. So we looked originally at this, probably the more common design would be you sort of stick with a single hub and you manage the complexity with service tags and try and take that as far as you can and deal with things like SNAT complexity. Or we could go a step further, which is, yes, you absorb a little complexity here on the spokes, and yes, you have a, let's say, a way of categorizing this option would be the default is you fail closed. If there's no non-standard config, you don't have access to on-prem. Whereas in this model, the default would be if there's no non-standard config, you have got access to on-prem, but you're broken when going to other PaaS services and anything that requires local breakout. So thanks for watching. It's probably not a pattern you'll find on the Microsoft website because it's more of a niche scenario which you come across more in certain verticals than not. But if you are wrangling with public IPs in your network and trying to connect to Azure, hopefully you found some value in this. Thanks a lot.